Good morning, everyone. My name is Ren Zhang. I'm a PhD student of COSIC and a researcher at Nervos. I feel a lot of pressure about giving a talk after Claudia because she can explain things in a very clear manner. Luckily, blockchain is young and very shallow research area, so that you don't. Hopefully, it doesn't take a lot of willpower for you to understand my talk. Bitcoin is the first decentralized digital currency. To run a currency, you need to answer three key questions. The first is who controls the money supply. In terms of gold, the money supply is controlled by nature. For fiat money, like dollars or euros, the money supply is controlled by the central bank. For Bitcoin, the money supply is controlled by the predefined rules in the source code. It's not mathematics. As long as all the Bitcoin users agree that we can change the total Bitcoin supply from 21 million to 42 million, it can happen. So whenever somebody tells you it's math, it's not. The second key question is who gets the new money. For gold, the miners or the government gets the new money, depending on the law, and whether the miners obey the law. For fiat money, the money supply, the new money goes to the banks. They have some responsibilities. For Bitcoin, whoever helps secure the ledger gets the new money. I will come to that later. The third key question is how to remember who has how much money. Oh, by the way, my slides are available online. If you want to go along with me, you can download it now. For gold, it's a physical possession. For fiat money, it's the numbers in banks or cash in your hand. For Bitcoin, everyone keeps a copy of the ledger, which is a really violent solution. What do I mean by everyone? So this is everyone. So everyone is 10,000 nodes distributed globally. Each maintains a full copy of the Bitcoin ledger. So what is the ledger? The ledger is a giant book recording who has how much money. In Bitcoin, the ledger is organized as an ordered list of transactions. If you look at this list, you can compute who has how much money. From the first line, the system creates 25 Bitcoins and credit to Alice. We know that Alice has 25 coins and no one else has any coin. After Alice transfers 17 coins to Bob, Alice has 8 coins and Bob has 17 coins. So when Bob transfers 8 coins to Carol, now Bob has 9 coins and Carol has 8 coins and Alice has 8 coins. This is the most complicated mathematics you will see in this presentation. But as you can see that if the transaction order is settled, we can determine whether a transaction is valid or not. Because at that time when Alice transferred 15 coins to David, Alice doesn't have that much coins. So we can know that this transaction is invalid. So I will introduce the design of Bitcoin in a Q&A manner. Sometimes answering one question may lead to more questions, but eventually all the questions will be answered. The first question is how to store the ledger. Bitcoin's answer is everyone keeps a copy. The second question is how to notify the others about the transaction. Bitcoin's answer is also very brutal and violent. It is broadcasted to the entire peer-to-peer network. Although the answer seems to be really ugly and inefficient, I think that is why no cryptographers before Satoshi Nakamoto come up with this design. It turns out as long as you have a system that is working, you can optimize it to make it more efficient and preserve the same security properties. But I won't have time to go into how to save the bandwidth consumption and save the storage. The third question is how to prevent Alice from spending Bob's money. Bitcoin's answer is that the transaction must be signed by the sender via digital signature. Let's take a deeper look inside the transaction. For each transaction, it has one or more input, which is the sender of the transaction, and several output, which are the receiver of this transaction. And the total amount of input must not, total amount of output must not exceed the total amount of input. Otherwise, you are creating money from thin air. So inside a transaction output, it has two meaningful fields. The first is the hash of the public key of the receiver, so that we know that this transaction is intended for Bob. The second field is the value. For a transaction input, it has three meaningful fields. The first field is the pointer. It says, I want to spend transaction A, the first output of transaction A. It tells you which transaction output I'm trying to spend. The second field is the public key. It shows an external verifier that I am the owner of this public key. You can hash my key to check whether my key correlates with this hash result. The third field is the signature. Bob used its secret key to sign on the entire transaction, saying that I authorize this transaction. I agree with everything it says. Is that clear? Okay. So, more questions. So how to prevent Alice from spending the same money twice? Namely, how to maintain transaction order, and how to make sure people store the same ledger, and how to issue new money. Let's take a look at how the blockchain is extended. Blockchain is the data structure that stores the transaction list, namely the ledger in Bitcoin. First, new transactions are broadcast to all the nodes. And then each miner is a special kind of participant who contribute their computational power to secure the ledger. Each miner collects new transactions into a block. Third, in each round, a chosen miner broadcasts his block. We don't care how the miner is chosen at this stage. And next, other nodes accept the block only if all transactions in it are valid. A valid transaction means the outputs are unspent, the signatures are valid, and the total value of input is larger than or equal to the total value of output. At last, miners express their acceptance of the block by including its hash in the next block they create. Assuming most nodes are honest, a valid block would be accepted by most nodes. If the new block contains an invalid transaction, node will not include it in their blockchain, which answers the fourth and the fifth question. Is this clear? So, which raises a new question that how to choose that miner. We choose the miner via a process called mining. Every miner works on finding the solution nonce to the following puzzle. The hash of the transaction Merkle root and the previous block and the nonce is smaller than a predefined target. It's like finding a needle in a haystack. The only way to find a nonce that satisfies this equation is to enumerate this nonce until you find a value, and enumerate this nonce and compute the hash until you find a value that satisfies this equation. Because of the one-wayness of hash function, it's impossible to reverse the equation and compute the nonce directly. The target is dynamically adjusted so that on average a block is found by the network every 10 minutes. Whoever finds the solution first broadcasts the block, and the probability that a miner is selected is proportional to its computational power, which answers the question how to choose that miner. There's a security assumption, we'll come to that later, that no malicious party can choose more than 50% of computing power. Which raises the next question, because mining is very energy consuming, why would people want to be that miner? A coin-based transaction in a block has no input and issues a fixed amount of mining reward in Bitcoins to the miner. And the difference between the inputs and outputs in a transaction are called transaction fee, which goes to the miner, which answers the sixth and the eighth question. So miners are incentivized to do the computation in order to get the block reward and the transaction fee. And the mining rewards halves every 4 years. As you can see, at the beginning, at the 4 initial years, you can get 50 Bitcoins from mining one block. And then it was 25. Nowadays, it's 12.5. Now we have 17.7 million Bitcoins mined out of the 21 million total. In around year 2140, no new Bitcoin will be mined. Of this 17.7 Bitcoin, less than 4 million of them are considered lost. So let's look at a graphical view of the ledger. So in each block, the transactions are organized in the Merkle tree. And to compute the hash of the block, you only need to put the Merkle root of these transactions in the hash, in the preimage. Having this Merkle tree structure has two benefits. The first is that if you update a transaction, there's no need to compute the entire hash. You only need to compute the hash along the path. The second is that even if you change a single bit in a single transaction, the Merkle root will be changed, so that as long as you have the root, it actually authenticates all of the transactions in the block. As I said before, in every block, it contains new transactions half of the previous block and none, so that the hash of this string is smaller than the target. So as long as the miner finds a block, it broadcasts it to the network. And hopefully, the next block will include the hash of this block in its block header, so that it expresses, I accept this block. Currently, the blockchain is around 210 gigabytes. Which raises another question, that what if two blocks are found simultaneously? We call that situation a block fork. Bitcoin protocol prescribes miners to choose the chain that is most computationally challenging to produce in case of a fork. So which chain contains the most computational power? I consider that chain to be the authentic version of the history, which is usually the longest chain. But when evaluating the computational power of generating a block, they actually use the expected number of hashes. For example, 2 blocks with target 10 equals 1 block with target 5. Consider roughly like it takes twice the computational effort to generate a block with target 10 to generate 1 block with target 5. That is like the usually referred to as the longest chain rule. Is that clear? Okay.
I have another question. How many transactions are included in a block?
Around 2,000 nowadays.
So if the longest is not the most computationally challenging,
Choose the most computationally challenging.
okay, so longest is approximate.
Right. Longest is a rough expression. Or in a tie, choose the first received chain. So how often do block fork happen? Before July 2017, it happens roughly once per day. But as you can see, after this time period, some magic happens. And there's almost no orphan block. Why is that? Because of UASF movement, because Bitcoin was having a civil war at this time. So everyone was upgrading their clients to advocate that I support this side of the civil war. And these technologies to remove these orphan blocks are ready long before that. But before that, people don't upgrade their clients. So after this movement, people good things happens. So I'm really hoping for another civil war so that Bitcoin clients, people are incentivized to upgrade their Bitcoin clients again. Here's a picture of a mining farm. It's just a corner of the mining farm. Nowadays, it's infeasible to do Bitcoin mining on your laptop. And it is also not very advisable to buy a Bitcoin miner to mine for yourself, because these mining farms, they have like millions of mining gears, and their gear is usually faster than your gear. So it may take 1 million years for you to find a Bitcoin block. So as I said before, for a single input, the transaction is valid if it is signed by the private key of the input address. However, that is just the default case. The real case is that Bitcoin supports a script language. In each output and in each input, there's a tiny program in it. The output script says that you need to satisfy these conditions in order to spend this output. And the input script says, I am qualified to spend. The transaction is valid if and only if when you concatenate this script and execute the program, the output of the execution is true. So what are the possible conditions to spend a certain output. So here is a comprehensive list of the possible conditions. A transaction can be anyone can spend or no one can spend. It may be somebody needs to sign on the entire spending transaction, or k out of m people in this group needs to sign on the spending transaction. Or you need to show me the pre-image of this hash result in order to spend it. Or you need to provide a hash, you need to provide a script that hashes to this result and execute it. And only if the execution is true, you can spend this output. And time lock, it must be spent after block number n. So the possible spending conditions are arbitrary combinations of this one. You can say A and B, or C, or more complicated conditions.
The script, provide a script that hashes to this result and execute it. Is that script your transaction?
Sorry, the script is here.
So do you provide the script as your input to the? It's like instead of having a transaction that says sends 1 Bitcoin to this address,
right?
It says run this script.
It says for this transaction, it says send 1 Bitcoin to this P2SH address.
Okay.
For this transaction, it says I'm trying to spend this P2SH address. Here is the script.
I guess my question is, if the script is very big, where is this script living? Is it in the blockchain?
Here. The script is here. It's usually not very big because the programming language is very compact. Okay. But for Ethereum, it's super big. Right.
Okay.
That's why I don't like Ethereum. So let's recap. What is Bitcoin? Bitcoin is a peer-to-peer network maintaining a public decentralized ledger of transactions that transfer values in Bitcoin from one or more senders or inputs to one or more recipients or output. The integrity of the ledger is secured by miners. What do miners do? They audit transactions. They use proof of work to arrive at consensus about the transactions. And successful miners receive new Bitcoin as reward. So what's new in Nakamoto consensus? So blockchain is usually, nowadays, blockchain is just alias of consensus protocol. In the theory world, consensus protocol are defined with the following two terms. They roughly have the same meaning, so there's no need to distinguish them for this talk. For state machine replications, all nodes start at the same initial state and agree on a common sequence of messages. Each deterministically transfers the state and maintain consistency on the state. If you have a system that does this, it's a consensus protocol. So long before Bitcoin emerged, there is classical consensus protocol. You can think of classical consensus protocol, or you can remember classical consensus protocol as this fully connected graph of computers. Everyone is connected to everyone, and the connection is very reliable. In the setting of classical consensus, the total number of participants is fixed and known by everyone. And everyone knows everyone. Messages are sent either via secure connection, meaning that if I receive a message from this wire, I'm sure that this message is from you, or with digital signature. Digital signature is even stronger, that not only I can be sure that the message is from you, I can determine that this guy is the one who generates the message. And for latecomers, the authentic history is the majority version. If I want to join the network and I want to learn the history, I just ask everyone and see which version of the history is agreed by most people. And this means late. I don't have any better icon for that.
Byzantine protocol, Byzantine agreement can be solved without digital signature.
Yes.
There are some literatures, and
that's why there's an or here.
It's not necessary.
Right. Or if you don't have digital signature, you better have secure connection. If you have neither of them, then I don't know how it can be achieved.
I mean the time assumption.
we'll discuss that offline. I'm not an expert in this, so maybe there are some mistakes. And it achieves asynchronous timing assumption, meaning that the network delay can be unknown, which is a good thing. And its security properties are binary. Namely, the security of the system is either whole or broken. There's no middle ground. For open or permissionless consensus, the definition is the participants don't know the number of participants. We don't know how many people are in the network. And there's no node ID. And all the message initiators are anonymous, meaning that there's no one-to-one channel and all messages are broadcast. So what does that mean? What does that lead to? We already have a solution for latecomers. How do the latecomers tell the authentic version of the history? In proof of work, the authentic history is the one that is most difficult to compute, as I said before. So that's our answer. And what are the implications of this setting in these things? Can we get rid of proof of work? Researchers have proved that no, you cannot. Proof of work is needed without authentication, meaning that if you don't have authentication in a proof of stake system, then you are not secure. So all proof of stake system needs to introduce somewhat identity in order for it to be, for the latecomers to know. Can we get rid of proof of work after a while? No. Proof of work must be performed indefinitely with late spawning. Meaning that if you want the latecomers to learn the authentic version of the history, the proof of work can never stop. Otherwise, the attacker can secretly construct an alternative version of the history with more proof of work, so that to puzzle the latecomers. Is it possible to design an asynchronous protocol? Unfortunately, no. The network delay must be known if the number of players is unknown. Because if the network delay is unknown for certain groups, for certain nodes in the network, it can never know whether there are an alternative version of the history, but these nodes happen to be offline, or their network delay with us is incredibly long, or there isn't another version of the history. So you can never be sure that history is settled, because it may be just on the way here. Can we go beyond 51% assumption? No. Honest majority is needed with late spawning. So let's revisit this slide. If the participants don't know the number of participants, the protocol cannot be asynchronous. It needs to be stronger than asynchronous, somewhat synchronous. If there's no node ID and all messages are broadcast, some scarce resource is necessary. For example, computational power in Bitcoin's case. If you choose the authentic history as the one that's most difficult to compute, proof of work must never be stopped, and the attacker cannot go beyond 50% mining power. What about the security properties? The security properties look different. For permission consensus, security properties are binary. N is the total number of participants in the system. F is the malicious, the number of malicious participants in the system. As long as the total number is more than 3 times the malicious members, the security properties hold. But for permissionless consensus, if the attacker controls more than 50% of the mining power, the system is broken. But when the attacker controls less than 50%,
it's not shown in the left side. Only in the asynchronous or partial asynchronous, the bound is the 1/3. And if it's synchrony and authenticated in the permission consensus, you can achieve like half the majority honesty or
right.
one, but no.
This is just an example. So there are other constructions. And in permission consensus, there's no incentive. In permissionless consensus, it has incentive, but incentive system is easier to break than security. If you have correct incentive, it doesn't mean the system is secure. But if you have wrong incentive, you can conclude that the system is insecure. So let's take a look at several attacks against Nakamoto consensus. The first is selfish mining attack. In this figure, the red double line indicates the public network, and the red square indicates when a block is broadcast to the network. When the attacker finds a block, instead of publishing it to the network as the protocol prescribes, the attacker withholds it, hoping to mine on top of it and gain a larger lead on the public blockchain. So the next honest block will be mined on this block. At this time, the attacker broadcasts its block, hoping that the next block will be mined after the attacker block. If that happens, this honest block is orphaned. When the attacker finds more than one block in a row, the attacker is sure that this chain is secure. He will not release this chain until the lead is reduced to 1. Now the lead is 1, the attacker publishes all the blocks in this secret chain. Because this chain is the longer chain, all miners would mine on the attacker chain. By performing this attack, the attacker gains unfair block rewards. Namely, with 30% of the total mining power, you actually get 60% of the total mining reward, if I'm recalling correctly. And rational miners would join the attacker, which damages decentralization. Not 60%, it's 3 in 7, but doesn't matter. The second attack is called double spending attack. The attacker sends some money to a merchant and embed this transaction in the public blockchain, while secretly embed another transaction spending the same money but transfer the money back to himself in a secret chain. When the public chain reaches 6 blocks, the merchant will deliver the product because by convention, it takes 6 blocks to confirm a transaction. Only then the attacker releases the entire secret chain to invalidate the honest chain and reverse the confirmed transaction. In this attack, the attacker gets the product without paying for it. The third attack is called censorship attack or feather forking attack. In this attack, the attacker publicly claims that I will try to invalidate all blocks confirming these transactions. And if some miners do not obey the attacker's order, the attacker would try to orphan this block, despite the fact that sometimes the attacker may be in a shorter chain. Although the success rate of this attack is relatively low, rational miners would join the attacker in the censorship so that the attacker becomes a de facto owner of the system. All these 3 attacks roots in imperfect chain quality of Nakamoto consensus. What is chain quality? It is defined as the minimum percentage of main chain blocks by the compliant miners. It is not the reward. So the percentage of main chain block equals the percentage of reward in Nakamoto consensus, but not necessarily in other consensus protocols. Ideally, we want chain quality to be equal to the compliant miners' mining power. Namely, if compliant miners control 70% of the mining power, they should get 70% of the main chain blocks. However, by performing block withholding attacks, the attacker can lower the chain quality. In the above figure, without the attack, the attacker gets 2 blocks out of the 7 blocks, and the honest miner gets 5 blocks out of the 7 blocks. But with the attack, the main chain blocks reduce to only 5, and the attacker gets 2 out of the 5. Honest miner only gets 3 out of the 5. Because chain quality is not perfect, it leads to the 3 aforementioned attacks. Is that clear? I assume that is clear. So, solutions. Can we do better? So, many proof-of-work protocols have been proposed after Bitcoin's Nakamoto consensus. Each claims to achieve stronger security properties. However, we cannot listen to their self-claimed results. So the true question is there a consensus protocol that comprehensively outperforms Bitcoin in security? In our recent research, our recent research tries to answer that question. As I said before, the imperfect chain quality leads to 3 attacks. So a protocol claims to be more secure than Nakamoto consensus needs to either achieve better chain quality or resist better against all 3 attacks. Selfish mining resistance is measured by incentive compatibility. Double spending resistance is measured by subversion gain. Censorship resistance is measured by censorship susceptibility. Our results show that no protocol is comprehensively better than Bitcoin. For better chain quality protocols, some of them are comprehensively worse, and some of them only raise the attack resistance in certain attacker settings. For other attacker settings, they are worse than Bitcoin. For all these protocols that claims to achieve better attack resistance, they usually sacrifice one attack resistance for others. So it's hard to say it's an improvement in security. If you're interested, you can check our paper. So why is that? The first reason is cap theorem. In the distributed network, they have a result saying that for any distributed system, you cannot achieve availability, partition recovery, and consistency at the same time. There may be trade-offs between them, but you cannot achieve full score in all three categories. So all proof-of-work protocols favors partition recovery and availability over consistency. When the network is partitioned, for example, China and outside China are the network connection between China and the rest of the world is disconnected. You can imagine all the Chinese miners come up with a version of the blockchain. All the non-Chinese miners come up with another version of the blockchain, so that availability is preserved, but it has no consistency. Namely, the two versions may be different. And when the network is partitioned and reunited, the ledger converges fast. It's very easy to determine which version is the most computationally challenging to generate, and the other version is abandoned. This design choice leads to that chain quality attack and network partitions are indistinguishable in Bitcoin network. So when somebody suddenly sends you a blockchain with longer chain, you cannot tell whether this someone is doing selfish mining or block withholding attacks, or he just got offline for some reason. And all proof-of-work protocols try to be asynchronous. Namely, when the network delay raises, the number of confirmation blocks, the number of confirmation required for a transaction raises. So it doesn't specify that for this network delay, it is safe if you have 3-block confirmation. If the network delay raises, you need 6 blocks to confirm a transaction. However, the delay to confirmation equation is not part of the user's manual. It's hard to determine that with the current network delay, how many blocks should I wait? The second problem is information asymmetry. So the protocol cannot distinguish between honest and attacker blocks. Why can't they? Because the attacker acts on all available informations, which include local information, the secret blocks, mined by myself, and my system clock, and public and verifiable afterwards. Some information that are public and verifiable afterwards, like the public block content. And public but not verifiable afterwards, like the block publishing time. I cannot prove to anyone that the block is published at this time, after this time has passed. And the network condition, latency and the propagation advantage. I know my my block propagation is faster than 50% of the miners, but compliant miners only act on 2. So all this information are not incorporated in the consensus protocol. That's why the attacker always has an advantage in exploiting the protocols. And having a novel reward scheme does not solve the problem. We discover a dilemma called rewarding the bad or punishing the good. If you reward when two chains emerge simultaneously, if you reward all of them, there's no risk to double spend. Because no matter what I do, even if I fork the blockchain, I can still get the block reward. So if you reward all the blocks, you're actually encouraging people to do double spending attack. However, if you punish all the blocks, it actually introduces a new tool for the attacker to perform censorship attack. The attacker can say that if you don't obey with my censorship request, I will fork you, and the protocol will punish you for me. What's wrong with a novel reward mechanism is that the attackers may have different incentives. So there's no reward scheme to discourage all of them. So changing the reward scheme may help defend against certain attacks, but make other attacks worse. So how do we achieve better chain quality and attack resistance? You can discuss with me afterwards. So let's talk about privacy at last. There are 4 problems with blockchain and privacy. The first is called transaction graph deanonymization. Bitcoin is anonymous. Everyone uses a public key. However, that doesn't mean that I cannot link your real-world identity with your public key. I can link via the following method. For example, when you are spending 2 different public keys, I can immediately learn that because the teapot can only be used by one person, these 2 public keys must belong to one person. So I can link your public keys together. And when the teapot is 8.5 bitcoins, and I can immediately guess that this 0.5 bitcoins will go back to the sender. It's the change address, so that I can link these 3 public keys together. So you don't have unlinkability. The second problem is transaction value de-anonymization. If we mix a lot of transactions together, can we determine which input corresponds to which output? The answer is yes, and it's quite obvious because there's only one combination will give you a 20 Bitcoin input, which is when you're combining this and this. And there's only one combination will give you 10 Bitcoin, which is combining this and this. So if we don't de-anonymize the transaction value, even if there is a fancy technique that allows us to combine a lot of transactions into one giant transaction, you can still tell which inputs and which outputs are related. The third problem is network layer de-anonymization. The attacker connects to every node in the public network. And the first node to inform me a transaction is probably the source of it. So I can just by listening to all the traffic in the network to tell who is the sender of each transaction. The third kind of problems are related to smart contract. A smart contract is a computer program executed in a secure environment that directly controls digital asset. Here's an example of a smart contract. Alice will reveal to Bob a value x such that the hash result of x is the certain value. In exchange, Bob will pay $10 to Alice. If Alice does not reveal by July the 1st, she will pay a penalty of $1 per day that she is late up to $100, signed by Alice and Bob. This kind of contract is very convenient to deploy on the public blockchain because blockchain will protect the integrity of this contract, and it can be executed on the blockchain. But what are the downsides of that? Because in blockchain, everything is public, you cannot have sealed bid auction. So in a victory auction, the winner is the one who bids the highest, and the winner needs to pay the second highest value. But it's difficult to do that on the blockchain because in the blockchain, everything is in plain text. So the question is, do we trust the manager on choosing the winner, or do we reveal everyone's bid in the end of the auction? There's no perfect solution. You can also deploy Uber or Airbnb on the blockchain, but it has a privacy concern similarly, that my itinerary is between me and my driver. For the rest of the network, all you need to know is that this contract is executed correctly. It's none of your business. I shouldn't need to publish my itinerary on the blockchain. So what are the solutions? To hide the transaction value, the main idea is to encrypt the output values via a technique called confidential transaction. But it's not trivial to encrypt it. We need to preserve 2 properties. The first is the total value of inputs is larger than or equal to the total value of outputs, even after encryption. To solve that problem, we can use additive homomorphic encryption scheme. The second requirement is that all output values are small and positive, because we don't want someone to create a negative output value so that he can create money out of thin air by transferring a smaller amount to himself. The solution is to use zero-knowledge proof to prove that the most significant bits of the output values are zeros. Nowadays, such a proof is roughly 700 bytes. The first problem, how to hide the transaction graph. A very simple solution is Monero. For Bitcoin transaction, you can think of each transaction as a link between an output to spend and the new output. For Monero, it actually says I'm spending one of the potential output set. So for each output, I need to include several different outputs as my potential output set. And I can prove to you that I'm spending one of them without revealing to you which one I'm spending. And anyone can check that it's not in the spend output bucket. There's a spend output bucket. I will put a secret about my true old output in the bucket to prevent myself from spending this output twice. That if you spend the same output twice, you can catch me that you're spending the same output to prevent me from exploiting this potential output set mechanism. Is that clear? Use some magic of cryptography. So the problem with Monero is that the latest element in the potential output set is usually the true old output. So I can just determine that which one of these is generated the latest. And I can guess that the latest one is your true output with like 90% rate of correctness.
Why?
Sorry?
Why is it like that?
Because I don't know how Monero works now, but before, like they sample randomly from the old output set to construct this set. And if you sample randomly, most likely you will encounter that people just holding the cryptocurrency. They don't spend it, they just buy it and keep it in their wallet forever. And the people spending this output are always the same group of people. So very likely, if you're spending an output, very likely, like a few days ago, you're also spending something else. You're actually using the cryptocurrency. So that's why the latest output is very likely to be the real output.
Just to note, they changed that.
Okay, but they changed it to a more accurate distribution.
Distribution, yes.
Right. But still, like there are other ways to, via auxiliary information, to tell whether which one is the correct output. So Zcash is try to improve that problem, improve upon that problem. In Zcash, the potential output set is all the previous output. It's the entire set. It says I'm spending one of all the previous output, and anyone can check that it is not in the spent bucket. But this check is relatively slow comparing with other cryptocurrencies. And similar, same as Monero, I throw some secret about my true old output in the bucket to prevent myself from double spending. So Zcash and Monero have the same problem, that the spend output bucket is ever growing. One needs to keep track of the entire list of all the output that are spent. And it is quite cumbersome for a cell phone to maintain the ever-growing spend output bucket. So Qiskit is a new design that solves this problem. Instead of having multiple output to spend, it updates multiple outputs. Each transaction says, I'm updating outputs in the updated output set. I change their addresses and I change their balances. But you don't know which one I'm changing. Very likely, I'm changing only the balances of only one of them, but you don't know which one. But there's a problem that for a user that stay offline for a few days, it needs to go through the blockchain and download all the blocks and to check, like, what's the address of my current output? Because when I'm offline, somebody might change my address for me. And I need to enumerate all the possible values to see what are my balances. Because the attacker may transfer some money into my wallet, so that it's difficult for me to check what are my balances. So there's no perfect solution. There's room for improvement. For network level anonymity, there's a design called Dandelion. Because the attacker can just connect to everyone and listen to all the traffic. The solution for better transaction anonymity is that I first perform a random walk of a random number of steps, and then I broadcast the transaction to the network. Because the shape of this graph is similar to a dandelion, that's why they name it after that. For smart contract anonymity, there are many solutions. So here's one slide to summarize all of them. When you're trying to design smart contract anonymity solution, you're trying to answer the following questions. Who executes the smart contract? It may be a manager that is trust for privacy, but not trusted for correctness. It may be MPC, multi-party computation. It may be every participant that is related to the smart contract. It may be a trusted execution environment. It may be multi-party computation with a group of TEs. You can do arbitrary combination of this, and very likely these design choices are interchangeable for your design. The next question you need to answer is that what happens when things go wrong? Do the smart contract abort or get the correct result? Is the malicious party punished? Do we have to publish the contract when things go wrong? And the third question is the workload for an external verifier when things go wrong or things don't go wrong. From the highest to the lowest, the slowest solution is zero knowledge proof. It was zero knowledge proof to show that my result is correct. Or there's a simpler solution that I repeat the entire smart contract execution. When things go wrong and people have different opinions, I just abandon privacy and take the smart contract online for everyone to judge who is doing the malicious behavior or who is getting the correct results. A better design is to repeat the contentious step in the execution. When people have different opinions on the execution of a smart contract, actually there's no need to upload the entire smart contract on the blockchain. There will be a step where people disagree. You just upload this single step on the blockchain and ask people to determine that who is correct. And ideally, you can only verify multiple signatures. For example, when people have different opinions, I just ask the participants to vote. Which side gets the most vote is the authentic result. Or even better, you can aggregate the signature into one signature so that from a public perspective, whether it is a smart contract or a single output transaction, is indistinguishable. Ideally, we want to achieve this, but that is not very easy. And the real challenge after you select these combinations is the performance, how to get it run efficiently. To summarize, Nakamoto consensus is the first permissionless consensus protocol. We did a comparison of security assumptions and security properties between permission and permissionless consensus. And we introduced several attacks on NC and why they are hard to solve. And we discussed 4 aspects of blockchain privacy. By the way, to people from the industry, the most important question perhaps you want to ask is, do you need a blockchain? The answer is usually don't. Using an open or permissioned blockchain only makes sense when there are multiple mutually distrusting entities that want to interact and change the state of the system and are not willing to agree on an online trusted third party. So if the system has only one writer, you don't need a blockchain. If the system doesn't need a global state, you don't need a blockchain. If there's a trusted third party that is always online, you don't need a blockchain. So there are some other research areas of blockchain I don't have time to cover. If you're interested, you can talk to these people from COSIC. That's all. Thank you.